Hi class, so now we are in chapter 5.3. This is radiation measurement. In Japan, March 11, 2011, they suffered a earthquake of 9.0 and a tsunami, which ended up resulting in radiation leaks from a nuclear power plant, and there's damage. If you paid attention to the news, this city is just stuck in time. Everything was left right where it was, and people have left that part. And I'm not condoning it, but if you do searches on YouTube, you can see people who have actually snuck in to these areas that are off limits because of the radiation and how much it's still very high levels there. And this is what we're going to talk about, is radiation measurements. Excuse me. So first thing is a Geiger counter. This is a common instrument. It detects alpha particles, beta particles, and gamma rays. It consists of a metal tube filled with argon gas. Argon gas is inert gas. It means it's not reactive. If you have double paned windows that are newer, you have argon gas in between those double paned. And if you look, there's a little sign or something on the window. It'll tell you that. So this tube is filled with argon gas, and radiation will enter through one end, and as it enters, it will form charged particles with the argon gas. And what happens is these particles will produce an electric current, and that will be able to be read on a meter. So let's go over units for measuring radiation. There's a lot here. I'm not going to go really too much into it, strictly what the book covers. Of all the sections, this is the one I'm probably not going to put as much emphasis in. That doesn't mean you shouldn't look at it, but I feel like there's more to this than just the radiation measurements. I'd rather have you understand the actual radiation. So the first one is Curie. It's named after Marie Curie, the famous scientist who worked with, she worked with radioactive elements. And her daughter also went into this after. Marie Curie won a Nobel Prize. Her daughter also won a Nobel Prize, Irene Curie. And Marie Curie and her husband were the ones that did a lot of this research. Amazon has a movie on her that came out a couple months ago. I cannot remember the name, but if anybody's interested, let me know and I will look it up. It's with if you've seen that movie Gone Girl with Ben Affleck, it's his wife that disappears. It's her, Rosamund Pike, I think that's her name. Anyways, I'm getting off track. So the measurements are based on disintegrations per second. Remember, this is decaying, so that's where the disintegrations per second come in. And when we chemists use seconds, we use it as an S. We don't do SEC. That is wrong. I would mark you wrong if this was in person and I gave something on an exam. You have to use the correct units. So it's S for seconds. See, 1 second. The number of disintegrations that occur in 1 second for 1 gram radium is equal to 3.7 times 10 to the 10 disintegrations per second. Next one, like I said, I'm really going to not go too much into this. Again, not probably saying this not right. It's Becquerel. This is the SI unit of radiation activity. They call these activities. So just understand when they say measurements, they call them activities, which is going to come up later. And this is 1 disintegration per second. So 1 Becquerel is equal to 1 disintegration per second. Rad is radiation absorbed dose. So this is what's absorbed. Measures the amounts of radiation absorbed by 1 gram material, depending on what that material is, for instance, body tissue or an organ. REM is not sleep. It is the radiation equivalent in humans. This measures the biological effects of what type of radiation was absorbed. And gray, the joules of energy absorbed by 1 kilogram of body tissue, 1 gray equals 100 rad. Some of these are going to come up later. So the REM is the radiation equivalent in humans. So it measures, now alpha particles don't necessarily can penetrate the skin because paper coverings will stop that, but if they are ingested or somehow get inside your body, they can cause extensive damage. So the REM would measure that how much the damage would be. High energy radiation would also be measured. This is beta particles, high energy protons and neutrons that can travel into the tissue. And gamma rays, which, if you remember that picture, it could just go straight through a body, so it can do a lot of damage. Measuring radiation damage. So we need to determine an equivalent dose or an REM dose. So we take the absorbed dose, and then it's adjusted by a factor to determine the biological damage that's been done. And it doesn't really go into what this factor means, so I'm just going to leave it at face value. It didn't break it down, it just provided numbers, and we're going to accept it at that. So beta and gamma radiation, the factor is 1. High energy protons and neutrons, the factor is 10. And alpha particles, the factor is 20. All right, so again, I told you activity was going to come up. So the measurement is activity. They tend to call these units activities, so just understand that that's how they're calling it here. Common units, SI units, and then the relationship of how you get from one to the other. Absorbed dose is called rad, and it's in units of gray, and that's equal to 1 joule per kilogram of tissue, and 1 gray is equal to 100 rad. And then we look at the measurements for biological damage. We use REM, and that is in sievert with its SV, and 1 sievert is equal to 100 REM. These can be very confusing because this is what we're not used to covering in chemistry. But for chapter 5, whole bunch of new things coming up. All right, so measuring radiation damage. Foodborne illnesses caused by pathogenic bacteria. And if you've ever seen the news, Salmonella, Listeria, these E. coli, people have died from these things. It's serious. So the U.S. Food and Drug Administration has approved a dose of radiation. I don't even know if most of you knew that we have food that is irradiated. I did not before, so this was kind of interesting when I was reading this. It's approved a certain amount, which is kilogray, 0.3 to 1 kilogray of radiation. And the radioactive isotopes is either cobalt-60 or cesium-137. So what happens is that the food will pass through, and a series of racks of gamma rays will pass through and kill the bacteria. The food is not radioactive because it never comes in contact with the source. The rays simply pass through it, it can react with the bacteria, and it kills off or prevents the bacteria from reproducing. So I found this slide online. It talks about the radiation breaks the bonds in DNA, and that either causes the organism to die or it cannot produce. And in little interesting tidbits here, frozen food takes longer radiation doses, and the effectiveness depends on the organism's sensitivity to radiation. So if food is irradiated, it has this little mark on it, which I have not seen, so I don't know where. Your book really doesn't go into much context about this, but I thought this was interesting. I've never seen this mark, and if you guys go grocery shopping, look and see if you see this. I do not, and I buy strawberries and stuff all the time, and tomatoes. So tomatoes, blueberries, strawberries, and mushrooms are irradiated, and you can see the difference from one and the other one that's not been irradiated as compared to one that is. That's because the bacteria that will allow this to decompose, because that's what it feeds off of, is gone. It's been killed off. So without the bacteria, it's going to last longer. There's no damage to it. The mold isn't allowed to grow. And that's pretty much it with the food. But now that I know, I have yet to see that little emblem, but or I'm just not paying attention. So a dosimeter, if you have to work in where there's radiation, you have to put one of these on. It doesn't protect you. That is not what it's for. What it does is it does not provide protection, but it detects and measures the radiation exposure that has occurred. So let's say you were exposed to radiation. They can use this dosimeter to determine how much exposure you were exposed to. So these dosimeters, this is not in the book, what I'm about to tell you. These dosimeters contain crystals which are capable of trapping electrons freed by various forms of harmful radiation. These crystals can then be measured to determine the amount of radiation the dosimeter was exposed to. So if they have to go back to see what needs to be done to help you, this is what they're going to use. Again, doesn't stop protection-wise, but it protects you, but they can go back and figure out what's going on. And dosimeters detect amount of radiation from X-rays, gamma rays, and beta particles. Again, that information wasn't in the book, so I'm not going to expect you to know that, just what's in the wording in the book, but I figured if I'm going to bring this up, I should explain how this works. Okay, so most of us are exposed, if not all of us, are exposed to radiation pretty average. There's an average amount that we're exposed to. And I don't know if most of you guys will know that, even some of our countertops, they give off, small amounts of radiation depending on what type of rock you have. It's made out of. If you're using something, some of these, they have quartz, granite, and so you've got to look into that. I'm not going to go more detail, but even that can provide a small amounts of radiation. But some of these amounts are so low that they really are not a cause for concern. And let's take a look. So you can have, there's natural, resources, ground, air, water, food, wood, concrete, brick, and the doses that they provide. Medical, chest x-ray, dental x-ray, mammogram, hip x-ray. If you have x-ray, you get x-rays for your teeth. I just got them done last week. You are exposed to a certain amount of radiation. And then other sources, nuclear power plant. Would it surprise you that it's that low? They go to great extremes to make sure that the stuff doesn't leak. And unfortunately, what happened in Japan, nobody could have foresaw enough time, a 9.0 earthquake and tsunami. And even if they had, that is such a high number that there's not much that could have been done. And then television and air travel and radon, which, you should have your houses checked for radon under certain conditions. So radiation exposure, we are exposed every day to very low amounts, even natural occurring, buildings, food, water, even naturally occurring isotopes. Potassium-40 is a radioactive isotope, and in food. Cosmic radiation, there's a lot of the stuff that's been known about. They go to great extremes to protect us from a lot of radiation because it's damaging, and you don't want a population dealing with this stuff. It's very, very dangerous. So my mind went blank for a moment, but every day we are exposed to a certain amount of radiation that's just normal. Cosmic radiation from the sun. Unless you completely avoid the sun, you're going to have to deal with radiation. Okay, but radiation sickness. What happens if you are exposed? Well, they need to know how much you've been exposed to. The larger the dose, the greater the effect on the body. Now, this is where a term lethal dose for 1/2 the population. They just call it LD50. I work in a company. They are working in therapeutics and diagnostics, and they constantly are looking at LD50. That's not my part of the department. I don't do any of that stuff, but I hear them talk about LD50. That's the first question people will ask when they're looking at something pharmaceutical. What's the LD50? And that is exposure. Half of the people are going to die. I mean, not people, let's just say half. If you're given a certain dose of something, what is the LD50? Meaning, at a certain value, what is half the people? I know I'm not explaining this right, but 1/2 the population, what's that value that's going to take out 1/2 the population is a better way to put it. So 50%. So the example it gives here is that they have determined that 5 sieverts, if you give that to a certain amount of population, that's going to kill off 50% of the people with that dose. 50% of the people will survive. They're not talking about side effects and damage and what's been done to those people that are alive, just death. So if you give a certain amount of people, let's say 100 people, a dose of radiation in 5 sieverts being the value, they expect 50% of those people to die. That's the LD50. And that's, so here, if you look, table 5.6, lethal doses of radiation. And I'm not going to go more into this, but it's sad to see some of this on here. But this is reality. They need to know what the radiation is, the damage that it can be done. And when accidents like this or nuclear bombs go off, there are people that are constantly monitoring and want to know the effects of all this stuff that's been, done. And, history with all this stuff. So LD50, this tells you these values. If you're given these values, they expect half the population of that dose to die with this certain value. It doesn't say how much of the population, but whatever it is, if you give, for instance, 5 sieverts to 6 people, they expect 3 of them to die. So that's the LD50 of it. Okay, so let's match each property with its unit of measurement. So we have activity. Remember, that's units. We have absorbed dose, and we have biological damage. I'm just going to attach them so we can discuss this. Activity is Becquerel. That is a unit. They call it activity. Absorbed dose is MRAD. And then we have biological damage. The unit of measurement for biological damage is M. So I'm guessing it's milli-rem, and then sieverts on here. As you can tell, I'm not really, this is the least unit section that I want to focus on. Anything that's covered is in the reading and up here, but I'm not going to really get more picky. I would rather focus on the other chapters, but do not ignore this one. Go over it and understand what I've discussed here. But I'm not going to put as much emphasis on this chapter. And that's it. This section.